Okay, welcome back everybody. Today we're going to be covering aqueous solutions, the Chatelier's principle, equilibrium, and acids and bases. So this is going to be possibly a really long video, so just stay attentive and listen to everything I have to say because all this stuff is 100% going to be on your chem lab test. So we'll start off with some aqueous solution stuff, and the first thing to do with aqueous solutions is define what a solution is. So a solution is basically a mixture of a solute and a solvent. And look at that. We already have two new terms to define. Solute and solvent. So a solute is essentially the thing being dissolved. So this is a thing being dissolved, which obviously makes the solvent the thing dissolving. A way I like to remember is solvent has this NT at the end, and it helps me, okay, solvent, solving, because solving also has that N at the end. I know it's a little bit of a cringy way to understand, but whatever. It works. So when something is soluble, or basically something that is soluble will mean that something that is soluble means that the solute dissolved completely. Solute dissolved in the solvent. And insoluble is exactly the opposite, and I mean, come on, you should probably know this. Insoluble means solute did not dissolve. And to determine how much something's going to dissolve or not going to dissolve, we use the solubility product, equilibrium, which is not something we're going to cover right now. Dissolve. I spelled dissolve wrong. Let's forget about that and move on. So now we're also going to talk about, in this case, solutions. There's a lot of polarity that comes up where you need to understand what it means to be polar or non-polar. So a polar substance, basically why I'm telling you this is because like dissolves like. So in this case, polar molecules will dissolve, or polar solutes will be dissolved by polar solvents, and non-polar solutes will be dissolved by non-polar solvents. And obviously a non-polar solvent cannot dissolve a polar solute. That's a lot of polar, solvent, solute, so I'm just going to show it to you. So polar, I'm going to do this in red and blue because polar is like charged. Polar means that there's a strong electronegativity difference. Strong electronegativity difference. Another way I like to think about polar molecules is it's unbalanced, meaning like it's heavier on one side, kind of like a seesaw. If someone is sitting on half of this on one hand end of the seesaw weighing 60 kilograms, and the other person is weighing 40 kilograms, it's gonna tilt towards the 60 kilogram person. It's like gravity is having a higher effect on that person, which it is, right? Because I may, but there's that unequal force of gravity on that, and that's similar to what's happening with polar molecules. There's an unequal charge distribution among it. So for example, let's take water. This is our oxygen molecule, and we have our two small hydrogen molecules over here. And for this I'm going to use a stick and ball method because it's easy for me to show you, and we'll also talk a bit about the vectors that's influencing this. So in this case, it is completely it's completely polar because you see this has a positive partial, and this has a positive negative, partial negative. Not what is that? So that means that these things, these partial positive charges, will be attracted this way. So it'll be, the vectors would be this and this, which means that's the electrostatic force on that particle. So that creates more of a charge distribution over here on that on the oxygen. And if you think about it, it's impartial because, okay, let's line up these vectors together, okay? We have a charge going this way, which is that, and we have a charge with this vector. Let's break it down into its components of x and y. Okay, so in this case, notice that these two, the x forces, they'll cancel. So that means that there is no horizontal force that's being acted on. However, let's see what happens when we're talking about vertical forces. This is going forward or up in the y direction, and this is also going up in the y direction. Which means that if both of them are going in the same direction, they combine. So there's twice as much of a vertical force or a vertical vector over here. So there's an overall charge distribution which is causing this imbalance and a force to be acting, which makes it polar. Obviously, say other polar molecules can instead of being like, triatomic, it could be diatomic as well. So say we have carbon monoxide. We have a carbon atom over here, and we have an oxygen over here. And for this, I drew a space-filling model. So here, oxygen is a lot more electronegative than this carbon, which means that overall, this carbon is going to pull this way, which creates a polarity on that side. So there's also this asymmetry that's occurring, right? Which determines polarity. And obviously, nonpolar, I intuitively, you might have already got it, but nonpolar is basically stuff that cancels out. So nonpolar is little to no electronegativity, which, obviously, if you have your periodic table and it has the electronegativities there, you can assess it using just those numbers. But it's a lot better to pictorially and conceptually understand. So, for example, carbon-hydrogen bond, both are small atoms that have little to no electronegativity, so that will be a polar or nonpolar. Anything that's diatomic, and anything that's diatomic like this is going to be nonpolar. And there are some structures like VSEPR structures that are inherently nonpolar as well. So for example, if I had a trigonal planar structure where each of the arms was the same molecule, you're 100% going to have a nonpolar molecule because all those vectors cancel out. So I'm just to give you some examples of nonpolar and polar molecules. Let's take, for example, a what is this called? A butane ring. Or not a butane ring, a butane chain. So we have a butane over here, 4 C's, all of them have H's attached to them. I'm not going to fill them in anymore because, why not? Why should I? So since there's an equal amount of force of hydrogens on each of the sides, this entire molecule is going to overall be nonpolar. For example, let's take something else. AgCl or NaOH. How about that? We have a positively charged sodium ion, and we have a negatively charged OH. So here, look at that. We have a clear difference in electronegativities, especially because because it's ionic. So it's going to be anything that's ionic is also polar because there's that charge distribution. So I hope you guys understand the difference between polar and nonpolar. There's really not much else you need to know most necessarily about solutions except for unsaturated and saturated. So unsaturated means that solution is not full, which means the solvent could dissolve more solute. There's that breaking point of where solvent cannot dissolve, and that's also determined by KSP. On the other hand, saturated things are full, so solvent cannot dissolve as any more solute. Something that's supersaturated means that solute has already dissolved as much as it can, but since it's been heated, the properties have changed and you can now suddenly dissolve more solute. So as temperature increases, generally solubility will increase for most solids. Okay, so things that might affect the rate of dissolving. we have temperature. So if you're increasing temperature, particles are starting to move faster, which means that there are more interactions, and there will be more interactions to break down the solute into that liquid form. Stirring can also help move the particles. It generates heat, and also it makes kinetic energy. So when you're stirring, it's going to dissolve faster. Finally, surface area. So if we have more solute that is contacting the solvent, so say I have a large sheet of metal that's like put into, I don't know, like some type of sodium solution or something, I don't know, calcium or something that's like that will help it dissolve. If I place a metal sheet onto it, it'll be a lot more effective in dissolving than if I put like a metal sphere onto, my bowl of dissolving things like solvent. So other things that we already talked about, like concentration. I'll just touch on that once again. Concentration depends on two things, and what concentration means is how much solute per solvent is in a solution. So you can find concentration by percent by mass, percent by volume, parts per million, parts per billion, whatever it might be, and finally molarity, which is what we're most generally going to be using. So molarity is just a general term describing ratio of, why do I keep writing ration? Ratio of solute to solution. Yep. So basically what molarity, the equation is M is equal to moles per liter. So moles of substance, liter of solution. Okay? So if there's a higher molarity, that means there's a higher concentration of that. If there's a lower molarity, there's a lower concentration of that. And this is obviously seen that, okay, if moles goes up, that means molarity goes up. If molarity goes down, that means that either liters goes up, means there's more volume of solution, or this will go down. Okay? Other than that, calculating molarity is basically pretty simple. You have this moles. We know how to find moles from the previous video, and usually this will either be given, like the volume will either be given or the molarity will be given, and you'll have to solve for the other one. So for example, let's say let's take this example question. Say I had 0.047 moles of NaCl in 1250 milliliters of water. So we know our final volume and we know our moles, and say everything has dissolved, we want to find the molarity. So notice that all we have to do is set up M is equal to moles per volume. We know moles is 0.0047 moles. Now volume, remember you can't really put this in milliliters. You want to convert it to liters first because that's what it says over here. So it's going to be 1.250 liters of H2O. Now we just have to do this division. I'm too lazy to actually go ahead and do that. I'm going to approximate it to, it's a little bit less than 0.40047. I'm going to say maybe it's like 3 something probably. I don't know. I'm just doing this off the top of my head. Probably not correct. Anyways, but yeah, that is molarity. Then finally dilution. And dilution, this equation for dilution is going to come up once again when we start talking about titrations. So keep this in mind. Dilution basically makes a lower concentration solution from a previously high solution by basically adding more volume. So once again, let's go back to that molar equation. We have moles per liter. So to dilute it, we're decreasing the concentration by increasing the volume of solution. So a way we can do this, or a way we can assess how much I want to dilute something, is through this equation, M2V2. So that means that the moles will never change, right? So we're going to do M1V1, so we're basically moving this over here. It should be equal to what we have afterwards. So in this case, if we're diluting, we're probably going to add more volume, and we probably know these two, and we just have to solve for, you know, what's the concentration after the dilution. Okay, that was dilution. I know that was a little bit quick, but it should be easy to understand. So say I have 12 molar HCl, and I want to make 500 milliliters of, let's see, 0.25 molar HCl solution. Let's just call it stock. Okay, how much volume of HCl will I need to add to, or how much will I need to dilute to make that much? So let's see, we know M1, we know M2, we know V2. So, or sorry, we have, this is also, wait, hold on, I messed up a bit, sorry about that. This is our M2, and this would be our V1, because we're adding, we have 500 milliliters, we want to make that much of, or this would be V2, sorry. We want to make 500 milliliters of that stock solution. So we have M2 and V2. We want to make M1's V1. We want to get that V1. So how much HCl would I need to dilute? So we would have to set up 12 is equal to, I'm going to convert this to liters. So V1 times 12 is equal to 0.5 times 0.25. I can do that in my head. It's 0.125. Then solve for V1, and 0.125 divided by 12 is equal to, let's see, 1/8 over 12. So basically like 1/36 of a liter. I'm not gonna do that. All right, so that's what I had for you for aqueous solutions. So that's just an introduction. Let me know if you had any questions, and I'll be back shortly. Okay, and I am back, and we're going to go over acids and bases. And while going over acids and bases, we're going to touch on Le Chat and equilibrium. So first thing understanding acids and bases is that they are characterized by the pH scale. And pH stands for potential of hydrogen. So basically what that says is the amount of hydrogen that's created in solution determines whether something acts as an acid or a base. And let me just give you a qualitative understanding of an acid. So acids usually taste sour, smell funky, and if you touch it, you'll probably corrode. Your skin will corrode. If you have a base, they're most likely bitter, kind of like bleach, baking soda. We have soap. Blood is actually a little bit basic, while acidic substances are like citric acid, batteries, tomatoes, and finally we have something that's in the middle of both acid and bases. We call this amphipathic, not amphipathic. We call it basically neutral. Amphipathic is something else, but we call it neutral, which means it can act as either an acid or a base. So some things like that is like water. Water can be both an acid or a base in solution, depending on what it's reacting with. So the pH scale is a logarithmic scale that's based on a number, which gives, it characterizes everything as a number from 1 to 14. The less of a number it is, the more acidic it is, or the less basic it is. And the higher of the number, the more basic it is and less acidic it is. And in the middle of the range is obviously 7, and that's usually around the pH of where water is. So there's different definitions of acids and bases that old men have created. So let's talk about Arrhenius first. I have to remember how to spell his name. Arrhenius basically said that in acids form H+ in solution, while bases form OH- in solution. So what this means is when acids react or are put into a solution, it dissociates with the hydrogen that it's attached to, and that means that the solution is now formed H+. On the other hand, bases will usually have some type of hydroxide derivative, and it will form that hydroxide in solution. And then, okay, that's just an introduction to Arrhenius. We have Bronsted-Lowry, and keep in mind, like, don't get these mixed up. I've gotten them mixed up before. It's really often that people will get them mixed up because they sound very similar and they have the same underlying idea. So Bronsted-Lowry says that acids donate H+, while bases accept H+. And if you think about it, this acids donate H+ is really similar to acids form H+ in solution. So donate just means that you lose it, and that's what's happening when acids form the H+ in solution. Bases accept H+ is really similar to saying that, okay, I'm letting go of that OH- and I'm accepting that extra hydrogen. Finally, we have Lewis acids and bases, which goes into like some electron dot structures and Lewis dot structures. Basically, acids will accept electron pairs, getting rid of those hydrogen protons, while bases will donate their electron pairs so they can accept those hydrogen protons. So now getting into the nitty-gritty of the pH scale. So pH, it's a really mathematical notion of how we can determine something that might be so quantitative. So pH is equal to log of H+. So when I draw these brackets, I'm referring to the concentration. So the concentration of H+ in solution. So the pH is a logarithmic scale, and it will basically mean that the lower pH means it's more acidic, higher pH means it's more basic. So a pH of 2 is not like twice as large as a pH of 1. It's 10 times as large because it's logarithmic, and it's base logarithmic, meaning it's base 10. Right? So yeah, that's basically understanding. If I want to better understand it, that means that, say I had a pH of 1 is equal to negative log 10 of H+. Rearrange and solve. Let's first do negative of that, so we'll get 10 to the negative 1 is equal to the concentration of H+. And say instead we have 2, the pH to be 2. Then we get log base 10 of H+. We can translate that to become 10 to the negative 2 molar of H+. 10 to the negative 1 is greater than 10 to the negative 2, which means that more H+ is formed when pH is 1, meaning that it's 10 times as acidic. pH of 1 is 10 times as acidic as a pH of 2. Okay. So obviously with these acids and bases, we can further characterize them into strong acids and strong bases, and weak acids and weak bases. And strong acids, like the strong and weak argument, basically tells us how well the ions will form in the solution, or basically how it's going to dissociate. So strong acids and bases will completely exist as ions when put into solution, while weak acids and bases will dissociate or ionize a little bit, but will mainly stay in its acidic or basic form. So examples of strong acids are nitric acid, hydrochloric acid, iodic acid, hydrobromic acid. There's like 2 or 3 more, and those are the strong acids, but we'll go over them together. And strong bases are stuff that's from like group 1, group 2, added with a hydroxide. Okay, so basically the underlying thing is that weak acids and bases will partially exist as ions, but mainly remain in its regular state. Finally, we can talk about equilibrium. Equilibrium, this is probably one of my favorite things to talk about because it's like really cool. So equilibrium, basically, when we have a reaction occurring, it's not necessarily translating to just acidic acid-base reactions, but any reaction, there's going to be a point where there's a lot of like the reactants really react a lot. They form a lot of product, but naturally what happens is that the product then starts forming a reactant, kind of like a synthesis and decomposition. Like, they go together almost. Like, say I wanted to, I don't know, create water from hydrogen and hydroxide. It's going to start creating water, and then it's going to revert back to that hydrogen and hydroxide at some point. So that point where, and then after that, what gets even more interesting is that it continues going back and forth until it starts going together. But the amount of water or the amount of the ions, so the amount of product and reactants don't change, although the reactant is still happening. So that means that there's a net flux of zero of the forward reaction and the reverse reaction. So basically, when the forward reaction and the reverse reaction are occurring at equal rates in this closed system. And this can be represented by the equilibrium constant K. So every reaction has its own equilibrium constant, and the K kind of shows how fast it's gonna, not how fast, but which reaction it's gonna be favoring. Will it initially go towards the forward reaction? Is it gonna initially go towards the reverse reaction? And what's gonna happen? So a large K will favor a forward reaction, while a really, really small K will favor a reverse reaction. I'm telling you that this can be a little bit confusing. We'll just go over it really quickly. So say we had this reaction. A moles of element A will react with B moles of element B to form C moles of, here if I can select something, C moles of element C and D moles of element D. I'll add in this stuff. So say this is a reaction. So how we're going to represent the equilibrium is basically by giving a ratio of the product to the reactant. And this is how it's going to be done. We're going to have K is equal to, so this is big C times big D, and little c is, so these are the exponents. So the concentration of C raised to the exponent C, lower c, and the concentration of element D raised to the power small d, over A over to the power of A, and B to the power of lower b. So this will show that this is a dynamic way to show equilibrium, because it shows a ratio of the amount of product formed and the amount of reactant formed. And obviously, things are not always going to be in equilibrium to begin with. So what's going to happen is it's going to shift towards that equilibrium. And sometimes when there's a stressor involved, we're going to get a movement back towards equilibrium, which we'll talk about shortly with the Chatelier's principle. So in experimental situations, what researchers like to find is the product quotient Q. So this product quotient Q is a form of equilibrium reaction or equilibrium constant, but it shows where in the equilibrium it is at that certain point that they're measuring. So it could be that they essentially take the current concentrations, and then they find this equilibrium constant. And that's not necessarily equal to this K, because that's what happens when it's at equilibrium. So the Q basically says, it gives a number, and if Q is less than K, that means it's going to have to shift forward. So more forward reaction is going to occur. If Q is greater than K, that means that too much forward reaction has happened, and the reverse reaction is bound to be happening. So that's all I have really for equilibrium constant and Q. Let's see. There are multiple types of reactions you can have with just that acid and base stuff we were talking about, and net ionics. So these are called neutralizations. So neutralizations reactions are basically an acid reacts with a base to form H2O plus salt. And don't get me wrong, by salt I don't mean like sodium chloride. Obviously that is a salt, but salt more generally refers to an ionic compound. So for example, a neutralization reaction could be hydrogen chloride plus NaOH, which unfortunately does make H2O and salt. But you get the idea. So this H plus reacts with the OH, and the Cl will react with the Na. This anion cation pair will form this solid salt, and we'll have a liquid we'll have a liquid water. The net ionic for this would be H plus OH minus is making water. Why am I writing it like that? Because that's really what's changing. That's the only thing that's changing. Cl and Na are present in both of these. Cl is over here, Na is over here. They all are gonna they can both dissociate or ionize, which means there's no real change in them. However, H and OH, they're here on the reactant side, but they're not here on the product side, which means that's the only thing that's really changing. All right. Finally, we'll get to titrations and Le Chatelier. So titrations actually the experimental part of the chemistry lab test, which basically means that we perform a titration, which is let me get it. Yeah, so titrations basically we're trying to find out. We're trying to use this M1V1 equals M2V2 equation to find how much of an unknown substance we're going to need to add, like say volume or how much we have to figure out one of these constants basically using a graduated like an entire setup. So the equivalence point of a titration is when the concentration of hydrogen is equal to the concentration of hydroxide, which means that if both of those are equal, that means that the solution is completely neutralized. So we're going to be mainly working with strong acids and bases, which means that this equation over here, M1V1 and M2V2, will be used to calculate this endpoint that we're going to talk about soon. But usually if we're going to use something like a weak base and a strong acid or something, we're going to have to do a few ice charts and use their acid and base equilibriums. But I'll just once again reintroduce the titration. We're going to slowly add the solution of a known concentration to a known volume of a different solution. So we're going to know this, and we're going to know this. We're going to slowly be adding more of this substance. We're going to start knowing about V1 until we're going to notice an like a end point, which is basically where the color will change. The indicator is added to the solution, and it does not affect the reaction, but it basically gives a moment where the color changes, which indicates that titration is over. At that point, we'll measure this V1 and then finally solve for the concentration of this unknown substance. So that's titration for you. That's really all I have for you. The only other thing is Chatelier's principle, which basically means that if a system is at equilibrium, and if there's a change in the concentrations of each thing or of anything, or doesn't necessarily have to be a change in the concentration, it could be changing temperature, volume, pressure, the system will change to a new equilibrium, where the equilibrium constant is still the same, but it will change partially, and it will counteract this initial change. So, for example, if I'm increasing the concentration of a substance, the equilibrium will shift away from it. So, for example, if I'm adding more reactant, that would mean that I shift right way in the forward reaction and produce more product. Why? Because the extra concentration needs to be used up. If I decrease the concentration, it's going to shift towards it because the reaction needs to produce more substance to make up for what was lost. If I increase the pressure of the system, this is where it gets interesting. It goes towards fewer moles of gas. So why does this happen? For gas, pressure will increase as volume decreases. So it needs to move towards fewer moles of gas. And the opposite applies when there's a decreased pressure. Say we were to increase the temperature of the system, then it will move away from heat and energy. It will move towards an exothermic reaction. So sometimes the forward reaction could be endothermic, and the reverse reaction could be exothermic, and that's all determined by what we're talking about. It could also be vice versa. But if there's increased temperature, that means we're going to be favoring that endothermic reaction, because that extra heat and energy will need to be used up. And what the exothermic reaction does is it gives off heat or loses heat. If we were to decrease the temperature, we're going to do the vice versa of that. We're going to go towards the endothermic reaction, because we need to start creating heat. We need to use that heat. If we were to add a catalyst, there's not going to be any shift, because a catalyst only affects the rate at which the equilibrium is being assessed. So that's all I really had for you today. I hope that all made sense. Be sure to ask me any questions that you may have on whatever else we have covered. Aqueous solutions. I know this was a lot of stuff. Aqueous solutions, acid base, titration, dissolving, diluting, Le Chat, and a lot of ionization stuff as well. So hope that all made sense, and I'll see you in the next video.